Hi, I'm Ming from Shanghai University. Now I will present our work, Bridging the Performance Gap for Copy-Based Garbage Collectors atop Non-Volatile Memory. This work is done together with my colleague Yanfei Yang and my advisor Haibo Chen and Bing Zhao. Non-volatile memory is known for its features like non-volatility, like SSD and HDD, and byte addressability, just like normal DRAM device. But it's also known for its large capacity, power efficiency, and lower price. So it can be used as a large alternative memory device for DRAM. People can organize DRAM and NVM together to form a large capacity memory. This usage is welcomed by managed language, especially for applications already have large appetites for memory resources, just like Spark, Flink, and HBase. For example, Spark can cache its data structure RTD into memory. To support this usage, the OpenJDK community has allowed heap allocation directly atop NVM. This proposal, JP316, allows Java applications to allocate objects or large heaps atop NVM while maintain other data, just like metadata for classes and methods on DRAM. In this usage, most memory accesses will touch NVM instead of DRAM. However, NVM also have disadvantages, and prior work has uncovered performance problems of NVM compared with normal DRAM devices. The first one is the random read and sequential read operations. The latency is actually larger than DRAM. Secondly, both maximum read bandwidth and maximum write bandwidth is much smaller than DRAM. The third problem is the bandwidth asymmetricity. We can see that the maximum read bandwidth for NVM is much larger than the maximum write bandwidth. This leads to a problem that NVM is quite sensitive to workload. When the write ratio increases, when number of write operations increases, the overall bandwidth will drop dramatically. Now we have known the disadvantages of NVM, but the memory behavior of Java applications atop NVM is still unknown. So we have conducted some evaluation. We run Java applications atop a CPU with 28 physical cores and SMT enabled, and we use 6 Intel Optane DCPM devices to maximize the NVM bandwidth. We extract 6 applications from Renaissance and Spark. We also break the applications into 2 phases, APP phase and GC phase. And the results shows that the GC time is actually severely affected compared with the APP phase. The slowdown is 2 times to 8.25 times. As comparison, the access latency is about just 2 to 3 times. Before analyzing why GC time is severely affected, we will first give some background about the copy-based GC. It is a very important algorithm, and many modern collectors in managed languages are copy-based. For example, the G1 and PS in OpenJDK, and a Mach compact algorithm in a common language runtime in C#. A copy-based GC collects the heap by moving live objects together. After GC, it will organize the consecutive free space for fast memory allocation. However, since it needs to copy a lot of objects together, it will introduce large bandwidth consumption. The bandwidth is actually the culprit for the GC slowdown atop NVM. We use the page rank in Spark as an example. For the DRAM case, the bandwidth can increase during GC because it has not reached its limit. However, for NVM, although we use the same workload, the bandwidth does not increase but decrease during GC. So we need to understand why the bandwidth decreases during GC and why it reaches its limit. Now we will dive into details of the copy-based GC. We use G1 as an example because it's default in OpenJDK. It's region-based, which means that it partitions the heap into regions for ease of management. And it's generational, which means that it only uses a few regions for heap allocation, and those regions will be collected in most cases. This can avoid a whole heap collection and reduce the pause time. and it's also multi-threaded. Each working thread has its own stack, which store references to the heap region. And during working, the thread will use these references to process objects and find all live objects and copy them. By adding more working thread, the algorithm can reduce the GC pause time. The G1 algorithm on reference processing can be divided into 5 steps. The first step is to fetch a reference from its working stack and find the object it points to in the G1 heap. The second step is to copy the object from the current region to another region. And step 3 is to update a forwarding pointer in alt copy in its header. Next step is to inform other threads that its object has been copied, and other threads can avoid repeatedly copying this object. The fourth step is to update the reference, which originally in NVM with its new address. The fifth step is to find if the object contains unprocessed references to other live objects on NVM. If it does exist some unprocessed references, its reference will be pushed to the stack for future processing. Okay, after this object or reference has been processed, the working thread will repeatedly pop the reference from its working stack and process them until all objects has been processed. Okay, now we put the 5 steps together. We can see that all the 5 steps can introduce many read operations and write operations to NVM. If we consider more threads, then we will introduce many read operations and write operations. That is the main problem. The G1 algorithm mixes many writes and reads together. If we consider the previous figure, if we have many writes, then the bandwidth will be jobs. So we will propose design to separate read operations and write operations, and thus improve the bandwidth during GC. The first design separates the data update. We introduce a region write cache for NVM update. It maintains a one-to-one region mapping for NVM regions on DRAM. When an object needs to be copied, it will be copied to DRAM in the region cache instead of NVM. Before GC ends, all live objects will be contained in the region cache. At that time, those objects will be flushed to NVM. Note that also we use the non-temporal instructions to avoid because it's NVM friendly and it can maximize the NVM bandwidth. By introducing the first design, we actually split GC into 2 phases, read mostly and write only. In the read mostly case, the first step and the fourth step has been replaced with the write operations to DRAM. While in the write only phase, there will be only write operations to NVM. There will be no read operations interfere with write. So in these cases, we can maximize the bandwidth. However, there's still a remaining problem, the header update, which is the third step. So we propose the second design to reduce the header update. We introduce a header map to store forwarding pointers. That map is organized as a hash map, which maintains a mapping from old address and new address. When the GC thread wants to update the header, it will become an insert operation to the header map. The workflow is as follows. First, the header update will be hashed with the hash function and find the corresponding slot in the header map. And secondly, we use a linear problem to find the suitable slot to store the mapping. A third step, if we find that a slot is empty, we can store the map from old address to the new address in a slot. However, if we cannot find an empty slot, we will go to the NVM to directly update the header. Now with the second design, we can now modify the third step so that it modifies the header map on DRAM. However, since the header map is use linear probing, it can fail, so still some NVM will occur when the linear probing fails. Now we'll briefly introduce the evaluation. We use 26 applications in all from Renaissance and Spark. And the figure shows that the 23 of the 26 applications can be improved with our optimization. And for the average GC time reduction, we can reach 1.69 times GC time reduction if we use both two optimizations. And if we only use write cache, we can improve 1.17 times. We also notice that the performance gap between DRAM and NVM now drops to 2.28 times, which is close to the latency gap, which is 2 to 3 times. And for the bandwidth, the figure shows that we can increase the average bandwidth during GC by 55% on average. And the best bandwidth improvement would be 2 to 58 times. We also show an example, the Spark PageRank, to show how bandwidth changes during GC. For the vanilla case, there is only one phase and the bandwidth is not satisfying. And for our optimized version, we can clearly see that there will be two phases, the read mostly phase and the write only phase. And both phases the bandwidth in both phases can be improved. So the result shows that separating reads and writes helps. Okay, to conclude, the commodity NVM can be used as alternative memory devices, which is welcomed by memory-intensive applications in managed languages. However, GC performance actually suffers due to NVM's limited bandwidth. Our optimizations sufficiently utilize NVM bandwidth by introducing two designs, write cache and header map, to separate the read operations and write operations. Thank you. That's all.